Somewhere in the vast dark of our galaxy, engines spin at incredible speeds, blasting out beams of radiation, twisting space-time and crushing matter into forms we can barely imagine. These aren't black holes. They're not stars either. They're the twisted, spinning remnants of stellar death. We call them pulsars. And they're even more terrifying cousins, magnetars. What happens if one of these monsters turns its eye on Earth? Could it strip our atmosphere in seconds, tear apart satellites, end life as we know it? In this episode of Skyward Space Quest, we dive deep into the strangest and most dangerous objects in the cosmos. We'll meet the galactic reapers, explore what happens if one collapses, and ask the ultimate question, should we be worried? Let's begin. Imagine a star 10 times more massive than our Sun. It burns hot, bright and fast, until one day its core collapses under its own gravity. The outer layers explode in a violent supernova, leaving behind something incredibly dense. A neutron star just 20 kilometers across, but containing more mass than our entire Sun. Now spin that object at hundreds of revolutions per second. Magnetic fields, 1 trillion times stronger than Earth's. Radiation, blasting out in tight beams, sweeping across the galaxy like a cosmic lighthouse. That's a pulsar. Each pulse is a blip of high-energy radiation, reaching Earth across vast interstellar distances. Some pulse dozens of times per second. Others, called millisecond pulsars, spin nearly 700 times per second. Their accuracy rivals atomic clocks. Their energy output dwarfs entire planets, and they're everywhere. Since their discovery in 1967, we've found over 3,000 of these stellar remnants scattered across the Milky Way. At first, scientists weren't sure what they were. They labelled the first one LGM-1, short for Little Green Men, because the signal was so regular it seemed artificial. Turns out, nature can be more precise than any machine we've built. If you could compress Earth into the size of a pulsar, it would collapse under its own gravity and become a neutron star too. But the surface gravity would be so intense, a teaspoon of material would weigh about 1 billion tons. Let that sink in. One sugar cube from a pulsar would outweigh every building in New York City combined. Pulsars aren't just visual. Astronomers have converted their pulses into audio. The result? A hypnotic, otherworldly beat echoing across the stars. Bip, 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 bip. It's like listening to the heartbeats of dead stars. But not all pulsars are equal. Some are more powerful, more chaotic, more dangerous, and one in particular. It's different. It doesn't just pulse, it rips space apart. That's what we'll explore. Most pulsars rotate steadily, sweeping the cosmos with beams of light. But there's one type that refuses to play by the rules. It's unstable, unpredictable, and far more dangerous. We call it the magnetar. And it's a pulsar taken to the extreme. Imagine a magnetic field 1,000 trillion times stronger than Earth's. That's a 1 followed by 15 zeros. It's so intense that it can distort atomic structures, twist magnetic lines into violent knots, and even release energy through starquakes. Cracks on the magnetar's crust caused by magnetic stress. These quakes can emit more energy in 1/10 of a second than our Sun releases in 100,000 years. The result? A deadly gamma-ray burst that can travel across the galaxy, invisible to the naked eye, but capable of disrupting satellites and potentially affecting Earth's atmosphere. On December 27, 2004, a magnetar named SGR 1806-20, located 50,000 light-years away, unleashed the brightest flash of gamma rays ever recorded on Earth. For a brief moment, it affected our planet's ionosphere and temporarily knocked out satellite communications. And that was from half a galaxy away. If a similar blast came from a magnetar within 10 light-years of Earth, it could strip away parts of our atmosphere. and possibly sterilize the surface. Scary? Yes. Likely? Thankfully, no. Magnetars are rare. We've only confirmed about 30 of them in our entire galaxy. Still, their very existence proves that stellar corpses can be both beautiful and terrifying. Magnetars are believed to form when a very massive star goes supernova and leaves behind a neutron star with unusually high magnetic fields. Why some stars become pulsars and others become magnetars is still debated. It may depend on rotation speed during collapse, core mass, or even magnetic field alignment. We're still piecing together the puzzle, honestly. But there's one thing scientists agree on. When you're dealing with magnetars, you're dealing with the most dangerous magnetic monsters in the universe. And if you think they're scary now, just wait. What happens if one of these collapses into something even worse? That's what we'll cover next. We've seen what pulsars and magnetars can do. But what happens if even their incredible forces aren't enough to hold them together? What happens when gravity wins? The answer, you get something even more extreme. You get a black hole. A neutron star, including a magnetar, is held together by a delicate balance, gravity pulling inward and quantum pressure pushing back. But there's a limit. If the mass of the core exceeds roughly 2.5 solar masses, even neutron degeneracy pressure, the force that keeps neutrons from being crushed into each other, can't resist gravity. The entire structure collapses. The star is gone. What's left is a singularity, an infinitely dense point surrounded by an event horizon, a boundary from which nothing, not even light, can escape. This is how a stellar black hole is born. The collapse from a neutron star to a black hole takes mere milliseconds. Honestly, it's faster than the blink of an eye. And when it happens, the release of energy can be so intense it may trigger a gamma-ray burst, the brightest explosions in the universe. These bursts can release more energy in a few seconds than our sun will emit over its entire 10 billion-year lifetime. Let's be clear. If a magnetar collapsed into a black hole close to Earth, say within 100 light-years, it wouldn't pull us in. Gravity from a black hole is no more dangerous than the star's gravity before it collapsed, as long as you keep your distance. But the radiation from such an event? Well, that's another story. A nearby gamma-ray burst could strip away the ozone layer, blind satellites, and even trigger a global extinction event. Thankfully, most known magnetars are thousands of light-years away, so for now we're safe. Even more dramatic? When two neutron stars collide, a cosmic event called a kilonova. The result? A black hole, a flood of gravitational waves, gold and heavy elements flung across space, and an Earth-sized fireball that lasts days. We've already detected one. On August 17, 2017, LIGO and Virgo observatories recorded gravitational waves from a kilonova over 130 million light-years away. It was the first time we heard the universe's most violent collision. So, black holes are born from collapsed magnetars. But what happens when those magnetars survive just long enough to evolve? That's when we meet their more terrifying phase. Get ready. Magnetars are just the beginning. Pulsars are dangerous. Black holes are ultimate. But in between lurks something even more volatile. A being that's barely stable, barely holding itself together, and sometimes it fails. Welcome to the nightmare flare stage of the magnetar. Imagine the crust of a dead star, frozen, solid, and under unimaginable stress. Now add a magnetic field so twisted it starts to crack that crust apart. what you get is a starquake. A magnetar starquake releases energy in less than a second, equivalent to hundreds of thousands of atomic bombs. These events can send shockwaves through space, temporarily outshine every star in the galaxy, and disrupt Earth's ionosphere, as happened in 2004. That year, we saw a magnetar flare from 50,000 light-years away. It affected radio transmissions on Earth. Think about that. An explosion on the other side of the Milky Way briefly reached us with enough strength to interfere with our technology. Magnetars don't just emit energy, they rewrite the rules of matter. Under their influence, atoms flatten, becoming cigar-shaped. Electrons are forced into narrow paths. Matter behaves more like plasma than solid. In a magnetar's magnetic field, human biology would disintegrate. Even chemical bonds that hold our bodies together would snap like twigs. There is no shielding, no protection, only distance. What if we could harness it? A single magnetar could power the entire Earth for millions of years, if we could control its energy safely. Of course, that's science fiction for now. We're still struggling to protect satellites from solar flares, let alone manage the energy of a cosmic flare that could fry electronics from a galaxy away. But it's a fun thought. One day, maybe humanity will build energy collectors near dead stars. Until then, they remain distant monsters. Magnetars are short-lived by cosmic standards. Most become less active after 10,000 to 100,000 years. Their magnetic fields decay. Their flares weaken. Eventually, they settle into quiet neutron stars or collapse into black holes. But while they're alive, they are the most violent entities we've ever detected outside black holes themselves. Still wondering just how dangerous these are? Let's run the numbers. What happens if one comes closer? We'll calculate the threat in the next chapter. Magnetars are rare, they're also far away, but what if they weren't? What if one of these ultramagnetic Death Stars was just a few light years away? Let's run the math. Scientists estimate that a magnetar flare from a distance of about 6,500 light-years, like SGR 1806-20, would be, well, barely noticeable here on Earth. If one happened 1,000 light-years away, it could disrupt Earth's upper atmosphere. At 100 light-years, we'd be looking at serious ozone layer damage and quite possibly satellite failure. And if a magnetar flared within just 10 light-years, that would mean an extinction-level radiation event. So in other words, we really don't want one anywhere near us. For a bit of context, the nearest star system, Alpha Centauri, is about 4.37 light-years away. If a magnetar existed in that region and flared, it could, permanently alter Earth's biosphere. In the event of a strong magnetar flare within 10 light-years, Earth could suffer ozone depletion within mere hours. There'd be increased ultraviolet radiation hitting the surface, severe impacts to DNA in both plants and animals, satellite failure, power grid blackouts, and high-altitude radiation exposure for aircraft. Over time, all this could, unfortunately, lead to mass extinction, similar to some events hypothesized in Earth's distant past. Some researchers even speculate that a long-gone nearby magnetar might have contributed to one of Earth's ancient mass extinctions. Fortunately, we're not flying blind here. Instruments like NASA's Fermi Gamma-Ray Space Telescope, ESA's Integral Observatory, and the LIGO and Virgo gravitational wave detectors can, well, alert us within seconds of high-energy events. While it wouldn't really give us time to escape, it would allow researchers to study the event and protect satellites or astronaut missions in orbit. Still, prevention isn't really an option. Only distance protects us. The closest known magnetar candidate is called 1E1048.1-5937, located over 9,000 light-years away. That's a safe distance. Closer neutron stars exist, but they're normal pulsars, not magnetars. So unless something strange happens, we're in the clear, for now. So yes, magnetars are terrifying, but the universe is huge, and they are, thankfully, rare. But there's one more twist to this story. Can these monsters, pulsars and magnetars, have planets? Let's find out. It sounds like science fiction. Planets orbiting a dead star, especially one that emits lethal radiation pulses every second. But in 1992, long before we discovered planets around sun-like stars, we found something even stranger: planets around a pulsar. The pulsar is named PSRB 1257+12, located about 2,300 light-years away. Astronomers Alexander Wolszczan and Dale Frail detected odd timing variations in the pulsar's signals, not from starquakes or interference, but from tiny gravitational tugs. Tugs caused by orbiting worlds, 3 confirmed planets around a pulsar. These aren't Earth-like oases. Pulsar planets are bombarded by intense radiation, tidally locked or rapidly spinning, possibly made of exotic materials and, well, lifeless, at least as we understand life. One of the planets, PSRB 1257+12b, is only about twice the mass of the Moon. Another, PSRB 1257+12c, is 4 times the mass of Earth. They may have survived a supernova or formed from the wreckage of the star's death. Either way, they orbit an undead spinning monster, and they are real. Could anything live there? Maybe. If a planet had a very strong magnetic field, a thick subterranean ocean, or was shielded by natural elements like ice, lead or water, then, in theory, microbial life could exist deep below. It wouldn't be life as we know it. But in the extremes of the universe, life finds a way, sometimes. And if advanced civilizations existed far beyond us, maybe they'd harness pulsars as navigational beacons or even power sources. A few scientists have speculated that some pulsar regularity could even be signs of alien tech. But that's a story for another time. Another famous pulsar planet is PSRB 1626b, nicknamed the Genesis planet. It's located in a binary system, 1 pulsar, 1 white dwarf, and 1 planet orbiting both. It's over 12.7 billion years old, older than Earth, older than the galaxy's spiral arms. This is the oldest known exoplanet, and it orbits a system of stellar corpses. Planets around pulsars are rare, but they exist. And their discovery reshaped astronomy. Before PSRB 1257+12, we didn't even know exoplanets existed. Now we've catalogued over 5,000, and it all started with a dead star. Even the galaxy's most dangerous monsters can still have companions. But does that mean we're safe? In our final chapter we ask, should we be worried? After all this talk of spinning neutron stars, radiation bursts and death beams from deep space, it's a fair question. Should we be worried? Let's be clear. There are around 3,000 known neutron stars, including a few dozen magnetars, in the Milky Way. But our galaxy is 100,000 light-years across. Most of these cosmic monsters are thousands of light-years away, and honestly getting further. The closest known magnetar is over 9,000 light-years from Earth. Even a super-powerful flare would barely nudge our magnetosphere. So, no, you're not likely to be vaporized by a random gamma-ray burst tomorrow, but the universe is unpredictable. Every once in a while, something truly rare happens. A rogue magnetar, a nearby supernova, a long-range gamma-ray burst aligned just right. In 2004, we did experience a real magnetar flare, SGR 180620, over 50,000 light-years away, briefly disrupted Earth's atmosphere. If it had been just a few hundred light-years closer, the effects could have been catastrophic. So yes, it's possible. Just very unlikely. If a magnetar ever threatened Earth, would we even know in time? Maybe. We have gamma-ray detectors, solar observatories and early warning networks for extreme space weather. But once a flare begins, it travels at the speed of light. By the time we detect it, it's already here. So our best defense? Understanding distance, preparedness. Despite all the dangers lurking in space, Earth exists in a relatively quiet region of the galaxy. We orbit a stable star. We're far from any known pulsars or black holes. Our magnetic field shields us, and our atmosphere protects life. That's rare, that's precious. Pulsars and magnetars are reminders of the universe's extremes. They're engines of destruction, relics of violent death, beacons in the blackness. But they're also natural, part of a galaxy in motion. We study them not to fear, but to understand. Because every time we learn about the cosmos, we learn a little more about ourselves. The universe is vast. It's dangerous, it's beautiful, and we're just beginning to explore it, like and subscribe to Skyward Space Quest.